Hello there, RJ. I'd like to introduce you to my crazy creation here, BARNDLES. BARNDLES, once it's finished, is going to be a fully functional microprocessor implemented in the shader editor of Blender 3D, which if you're not familiar with Blender, it's basically a 3D creation suite. You can create 3D models, textures, sculpts, renders, basically anything 3D computer graphics, Blender can handle it. But of course, I'm not doing anything with computer graphics. Instead, I'm building a microprocessor because I thought it would be a fun way to test my computer architecture skills and also add some additional challenging constraints that I have to work around, which I'm always open to playing with. So anyway, let's go ahead and get started talking about BARNDLES here. So before we actually execute any sort of instruction going through BARNDLES, I want to show you this graph that I put together here or I guess a flow chart of how information propagates through BARNDLES. The part that you're seeing right now with all these nodes is the shader editor, or the CPU, which is the main forward processing component of BARNDLES. So BARNDLES, because the shader editor here can't have any sort of feedback loop, it's exclusively forward processing, we can't actually put memory in this part of BARNDLES. Instead, we have to store it outside of it in a memory image. Now, when I say a memory image, I mean literally it is an image file. It's a PNG file, it's 64 pixels by 64 pixels, and each pixel encodes a 24-bit word in its red, green, and blue channels. That's actually this image you're seeing up here. This is just a piece of test memory I put together for testing purposes. So anyway, once this data is read from the memory image, I should also mention that the memory image contains all memory, including the register file, the data memory, the stack, the instruction memory. So once all of this memory is read from our memory image, it is passed into the shader editor here, where it then propagates through all this forward processing logic until we get to this material output node over here, which basically takes all of the shader data that we computed in here and outputs it to Blender's Cycles rendering engine, which is a path tracing rendering engine, which will render out an image, and then it saves that image back over our original memory image. So basically, every single time that we execute an instruction with BARNDLES, we go through this process. We read our data in from the memory image, we process it with the shader editor, we render it out with Cycles, and we write it back over the memory image. So let's go ahead and actually execute an instruction with BARNDLES now. We aren't going to be reading the instructions from memory quite yet because this is functionality that I don't have implemented quite yet, but we can hand encode our instructions here. So this is my instruction encoder right here, and I have this gigantic table of instructions that we can choose from. So we'll start off with something simple. We'll say, let's do an add instruction. So the opcode for our add instruction is 2. We can ignore the immediate flag, the CPSR update flag, and the invert flag. We can also ignore the immediate field down here. What we really want to focus on is RM, RN, and RD, which is going to be the first operand register, the second operand register, and our destination register. So in our first operand register, I should, I guess, focus more on our memory image here. Down here in the lower left corner, we have this bottom bar. These bottom 15 pixels directly correspond with the first 15 registers of our register file. So the 0th register is right here, and the 15th register is all the way over here. Now, although these appear to be black in the image editor up here, these actually hold different values. You can see that down at the bottom of this window here, we see the blue channel changing. This is actually because each of these registers holds a value that corresponds with the number of register it is. So basically, register 0 holds the number 0, register 3 holds the number 3, register 5 holds 5, so on and so forth. So if we wanted to add the values in register, let's say register 5 to register 3, we can add these two together, which will be 5 plus 3 because the registers hold the values that they're ID'd with basically, and we'll store the result in the 0th register. So we'll add the 3rd and 5th register and store the result in the 0th register. And basically what's happening now is this information is propagating all the way through our shader editor here, and it's being output to the surface of a plane, an actual image plane here. If we look at this is just 3D geometry, and it's rendering out the actual live preview basically of the calculation. Now we're not going to see any sort of vast difference in this just because, well, I mean, already look down here, the values are so small that you can't even notice them. So we're for sure not going to notice them in here. But when we bake this, or render it basically, out to another texture down here, we can take a look down at that 0th pixel where our data should have been written, and we'll notice that it's no longer 0. Instead, the blue channel has a value of 0.03137. Now, if we convert that from a floating point number to an actual 8-bit RGB value, I guess actually just a blue channel value, this is 0.03137. 0.03137, and we multiply that by 255, which is the 8-bit maximum, we get a value of 7.99935, or 8. And if you remember earlier, we added the values in 5 and 3, which adds up to 8. So we've successfully stored those into our new memory image, and we could then save this memory image back to overwrite the input memory image up here. Now let's try something else. Let's try a little bit more complicated instruction. We'll try a logical shift left. The opcode for a logical shift left is 12. And in this case, we're going to be shifting the value of 5 left. Maybe we should do 4, or maybe even 5. I guess we'll go with 5 because you can actually start to see down here the actual pixel being written in our preview. So let's go ahead and render this out. So I will select my output node really quick here, make sure that's selected so we don't overwrite our input data. And if we bake this now, we can see that we are given a value of, a blue value of 0.62745. So if we come into here and say 0.62745 times 255, we get a value of 160, which is going to be the equivalent of 5 shifted left 5 times, which if we look at this in the programmer calculator here, we had the output of 160. If we look at our actual bits here, we can see that it is in fact 5 shifted left 5 times. So there you go. Those are two very basic operations. Ideally, what is going to happen next with this is I have to implement the actual the program flow basically. So right now I'm just manually putting in instructions. Eventually, the entire top part of this image will be occupied by actual instructions, and it will automatically go through frame by frame, automatically calculating and executing those instructions, writing back to that image file, and executing the entire program until it gets stopped. So this is the current state of Barndles. Hopefully you enjoyed this overview. I know it was kind of a lot of information, and the video actually ended up coming out a little bit longer than I anticipated, but hopefully you stuck around and you enjoyed looking at this crazy project I'm working on. Anyway, it's been great talking to you, RJ. Thanks for showing interest, and I look forward to talking with you more in the future. See you around.